In order to achieve the Sustainable Development Goals set by the United Nations, it is essential to have access to good quality water and to protect its value. This is one of the key concepts of Goal 6, safe water and sanitation. It means pure water and hygienic services for everybody. However, it is also an essential prerequisite for many other goals. Zero hunger, good health and well-being, sustainable economic growth, reducing inequalities, and protecting marine ecosystems. In this lesson, we will examine the links between water quality and its uses and analyze the causes of its deterioration to understand how climate change exacerbates existing quality problems and creates new ones. Water quality is not an absolute value, but rather a relative one. In fact, it depends on the specific use you intend for it. Water may be of good quality for one purpose, but not for another. To assess water quality in relation to different uses, a series of physical, chemical, biological, and ecological parameters are considered. These parameters have been identified and regulated by scientific bodies and national and international institutions based on environmental and health studies. Their relevance varies depending on the function of the water: ecosystemic, environmental, for irrigation, recreational, potable, or industrial purposes. Let's take a look at them together. The main reference parameters for the ecosystemic function and the life of aquatic organisms are salinity, pH, dissolved oxygen, absence of toxicity, and temperature. For recreational bathing, the main parameter is the bacterial content. For potable uses, the law requires the absence of pathogens, absence of turbidity, negligible presence of harmful substances, and various other compounds. For industrial uses, finally, quality parameters are specific and vary from case to case. In this case, it is quite common the need to reduce or eliminate salinity in water supplied. In water intended for steam generation, dissolved gases must also be removed to prevent corrosion. The composition and quality of water depend on its history. In fact, during its incessant cycle, water becomes enriched and contaminated with substances of both natural and human origin. This happens as it passes through the atmosphere, while it flows over the ground and infiltrates the subsoil, and finally when it mixes with other waters. The quality then changes as a result of use. For example, after domestic use, drinking water becomes wastewater that is discharged into the sewer system. Most natural constituents are not harmful to humans or ecosystems, except for certain metals such as arsenic and fluoride, or pathogenic microorganisms or toxins produced by algae. The impact of human activities on water quality is much more significant and is determined by the combined effect of the introduction of pollutants discharged and the large-scale withdrawal of water. Contaminants can originate from point sources, such as industrial discharges or localized spills, or from diffuse sources, related to the transport of pollutants by surface runoff or underground infiltration. Pesticides, microplastics, mineral oils, and nitrates are examples of contaminants mostly coming from diffuse sources. Point sources can be generally well controlled and in developed countries have been significantly reduced thanks to the presence of efficient treatment plants. Controlling diffuse sources, however, is much more challenging because they originate from a multitude of sources scattered across the territory, often not directly identifiable and therefore more difficult to reduce. Therefore, even in the most advanced European countries, the quality of surface waters is often compromised due to the pressure exerted by diffuse sources, which affect a high percentage of water bodies. The situation is even more critical in less developed countries, where the problems are often more severe and widespread. The quality of surface waters is further threatened by climate change, the effects of which vary depending on the geographical area and are already partially observable. The main causes are rising of water temperatures, changes in precipitation patterns, and the expected rise in sea level. The increase in temperature has direct consequences on freshwater ecosystems, as it promotes dangerous algal blooms. Furthermore, it reduces the amount of dissolved oxygen in the water, threatening the life of organisms that depend on high concentrations of oxygen to survive. Changes in precipitation patterns then affect water quality in various ways. Heavy rainfall increases diffuse contaminant loads, as the flowing water has a greater capacity to transport pollutants. During periods of drought, on the other hand, water flow decreases or disappears entirely. As a result, contaminants from point sources become more concentrated in water bodies. In both situations, negative impacts can occur on the efficiency of treatment plants and on the suitability of waters for recreational bathing. In the case of floods, there are even greater risks due to the presence of sewage containing pathogens, waste of all kinds, and chemicals that may be released from ruptured tanks. The rise in sea level increases saltwater intrusion into aquifers, making them less usable or even completely unusable as a source of drinking or irrigation water. The die-off of 360 tons of fish that occurred in 2022 in the Oder River, which flows through Central Europe, is an example of the perfect storm created by the combined effects of human-caused pollution and climate change. The direct cause was the toxins produced by the rapid bloom of the alga Primnesium parvum. However, this bloom was caused by the combination of several factors: low water flow, low dilution in the river due to a prolonged drought, high water temperatures, and a large unexpected discharge of nutrient salts, probably originating from mining activities. To improve the quality and resilience of water resources, it is necessary to reduce pressures and mitigate effects, but also to expand analytical and forecasting capabilities by identifying the most vulnerable water bodies and assessing the likelihood and consequences of expected quality deterioration in various scenarios. This framework will serve as the starting point to develop the mitigation solutions, including reducing the main diffuse sources of contamination, as well as upgrading and enhancing water treatment plants to make them more resilient to threats caused by climate change.